I'm recording this lecture because I failed to the previous one. All right, so the goal today is to talk about polynomials of degree bigger than 3. And we've done lots of things with polynomials of degree 2. We know how to graph them. You can start with completing the square, go from there. We know how to find their roots. Because of, again, completing the square, you have a quadratic formula that tells you the roots. If you want to optimize, well, completing the square does that for you, right? Because it tells you the vortex formula. If you want to solve an inequality involving a degree 2 polynomial, well, start by solving equality, and then get the intervals by using those endpoints. Excuse me. Well, what about things of degree bigger than 2? Now, in truth, things of degree bigger than 2 are just much harder. But let's see a reason to care about them first. So here is a super easy example where a polynomial of degree 2 will come up, and hopefully it'll feel reasonably natural. So let's consider the following situation. You start with a 3x2 sheet of cardboard. We can put some units on it. Maybe that will help. Let's start with a 3-foot by 2-foot sheet of cardboard. Then we'll take a little cut out of each corner. We'll take a little X by X cut out of each corner, giving that little pseudo plus shape. Then each of these flaps on the plus, we'll fold them up. And we'll like glue this end to that end, this end to that end, this end to that end, this edge to that edge. And what do we have at the end? We'll have a box. Question 1. Find a function that models the volume of that box in terms of the size of each gut. And you know what? I think this is a reasonable thing to start as a warm-up exercise. Think about the geometry of this. The volume of a box is the product of its 3 dimensions. It's the length times the width of the box times the height of the box. So take a moment, try to work out what the volume of this box is in terms of this variable x. And you know what? Let's try to walk it out one step at a time. Let's do walk together. So first, let's try to figure out the length of the box. So I guess the length of the box will be like whatever this dimension is. That's right. I'm going to start with this plus size sheet of cardboard. I'm going to fold up those edges. That'll leave me left with that as one of the faces. So this blue length will be one of the 3 dimensions, which for now I'll call length. So what's the dimension? What is the length of this box after you do this cutting and folding? Well, let's think in terms of, I guess, like subtraction. This whole side length is 3, right? 3 feet or whatever units you want to walk in. Then the fold we'll reduce it by x on this side. And it'll reduce it by x on that side. So what are you left with? You're left with 3 minus x. The length of this box is, parentheses, 3 minus x. And the parentheses are important because I want that whole thing to be multiplied by something else. What about the width of the box? And I guess here by width, I mean that length. So it'll be
Would it be would it be 2 minus x for the width?
Yeah, I think they are catching an error that I made. I think it'll be 2 minus 2x.
Oh, yeah.
And I made the same error in what I wrote down. So you'll cut out an x here and an x here, 2 minus 2x. And what about the height of this box? I think it'll just wind up being this length x that you fold up. So at this point, we have a function that models the volume of this box. So here is a model for the volume of this box. Maybe we'll consider domain. So certainly this x is the length of a cut. So that x is going to be bigger than or equal to 0. But you can't make a cut that's like super big. If that corner that I cut out has length like 25, then there's no box left. And in fact, the cuts are all overlapping. In fact, I think if the length of x is even like 1, then I'll wind up cutting everything out on that side, and there will be no box left. So I think there are the dimensions that I should think about. All right, so let's play this game. Let's suppose that I want to make a cut that maximizes the volume of this box. If this were like a degree 2 polynomial, we could find that on the nose. Some techniques that you'll learn when you take calculus let you find the maximum on the nose. But without those techniques, we do still have one powerful tool. We can graph. So let's look, at a graph of exactly this function. Let's try to maximize. And unfortunately, I don't know how to like split screen or do anything fun like that. So I'm going to make that go away. 3 minus 2x, 2 minus 2x, x. Excuse me. Ugh. So let's graph. Don't need those. Parentheses, 3 minus 2x by 2 minus 2x by x. And let's adjust this viewing window a little bit. Lost an x. So there we see this viewing window. And let's see what we see. I see, yeah, you can see that. At 0, the volume is 0, right? If you don't make any cuts, you don't have a box. If you make a cut of length 1, your box is folded up to just an edge, so there's no volume again. It looks like the maximum volume you get is a volume of about 0.4 feet cubed, I guess if we're walking in feet. And you do that by making a cut of length about, nope, maximum volume is around 1.05. You get that maximum volume by making a cut of around 0.39 feet. So let's write that down. By looking at a graph, by graphing, the max volume seems to be about 1.06, 1.06, and you get it at an x value of about 0.39. Nice. So here's the payoff. High degree polynomials come up naturally. If you want to walk with anything in dimension 3, which is where we live most of the time, you need to be able to cube things. You need degree 3 polynomials at a minimum. There are lots of other physical applications where polynomials of degree 4 or 5 or higher come up. So you need to be able to deal with them. And I've been saying the word polynomial and degree a lot, but I haven't actually said what any of that means. So let's say what that means. And let's say by example. Let's start with degree 2. Degree 2 polynomial is something we've seen a lot. A degree 2 polynomial is anything with form ax squared plus bx plus c. Fair enough. And let's walk backwards from there. If that's a degree 2 polynomial, well, it's degree 2 because of that squared on the x. A degree 1 polynomial is the same, but the degree is down by 1. Ax plus b. And why is that degree 1? It's because x is the same as x to the 1. So the biggest power you see on the x is just 1. A degree 0 question? Okay. A degree 0 polynomial is just a constant. So like 5 is an example. Any constant is a polynomial. It's kind of silly to think of it as one because it's much simpler than that. So there's going down in degree. Going up in degree, you just do the opposite. A degree 3 polynomial is a sum of a bunch of powers of x, where the biggest power you see is 3. A degree 4 polynomial is a sum of a bunch of powers of x, where the biggest power you see is 4. So maybe one example here, 4x to the 4th minus 7x cubed plus 100 x squared plus 2x plus 17. There's an example of a degree 4 polynomial. It's degree 4 because of that power 4. Cool. So I think we're ready to write down a definition. In general, a polynomial is a function that can be written as a sum of constant coefficients multiplied by non-negative integer powers of x. So a polynomial is any function that can be written as a sum of a bunch of constant coefficients multiplied by non-negative integer powers of x. One example might be 25x to the 75 minus 24x to the 70 plus 3x to the 19 minus 2x plus 5. Right? Because what do I see? I see a bunch of, ooh, let's color code a little bit. A bunch of non-negative integer powers of x. So I can think of that one as being x to the 0 times x to the 1. There's an x to the 19, x to the 70, x to the 75. And a bunch of constant coefficients multiplied by them. 25 minus 24 plus 3 minus 2 plus 5. The degree of a polynomial is just the largest power of x in that polynomial. So for instance, in this one, the biggest power I see is 75. So this thing, the degree is 75. So in order to iron out any possible questions, let's make a quick, let's ask some yes/no questions. So here are 6 functions. Let's one by one ask, are they or are they not polynomials? And I'll do at least the first couple in the form of some polls. So first one, is 5 a polynomial? Question mark. Yes. No. Save it and let's launch it. So you should all have just gotten a little poll in your window popping up. Tell me, is 5 a polynomial? All right. So it turns out this is one of those trick questions I like to ask. It seems an awful lot like you shouldn't think of it as a polynomial. It's a constant. But it is a polynomial because you could write that as 5 times x to the power 0. And let's go back and zoom out so we can see the definition. A polynomial is any function that can be written as a sum of constant coefficients multiplied by non-negative integer powers of x. Well, that 0 right there is non-negative and an integer power. This is a polynomial. This thing is a degree 0 polynomial. Cool. So next one coming along. So constants are polynomials. It's silly to think of them as polynomials because they're way easier to think about as constants, but they are classified as polynomials. End poll. New poll. Next one is 1 over x polynomial. And there's an extra 5 in this phrasing, but that's okay. Is 1 over x a polynomial? All right, let's talk about it. So that 1 over x, perhaps you could write it as x to the power -1. Maybe you would even write it as 1 times x to the power -1. And let's see if that satisfies our conditions. So a polynomial is something that can be written as a sum of constant coefficients. I see a constant coefficient of 1, that's good. Multiplied by non-negative integer powers of x. Well, -1 is not non-negative. This is negative. So I see a negative power of x. This is not a polynomial. There are some things related to polynomials that this is. So I'm going to drop some buzzwords which won't be relevant for today's lecture. It's an example of one thing that you can call it is a rational function. Which is a what we'll describe in a few days. If you like, a rational function is a ratio of polynomials. It's a polynomial divided by a polynomial. Another thing that you can call it is what's called a Laurent polynomial. And the Laurent polynomial is what you get if you take the definition of a polynomial and you get rid of this constraint that the powers of x be non-negative. But we're not going to study Laurent polynomials in this class. It's just not a polynomial. All right, cool. So let's go to one that is more direct. And I'm going to start being all right, this next polynomial. I've left out lots of letters, and part of that is because my keyboard has a funky thing where it doesn't like the letter X, letter O. This polynomial, well, I guess I just spoiled it a little bit. Is that a polynomial? Excellent. Yeah, of course it is. This is like a prototypical what is a polynomial. That is a degree 5 polynomial. Excellent. Right, it's degree 5 because the biggest power I see is 5. All right, the next one. X plus 1 over x minus 1 is this a polynomial? Cool. It turns out it is not. And let's think about why. So a polynomial is something you can get by a sum of a bunch of constant coefficients times powers of x. There we go. That's better. My internet connection is unstable. That's really good. So it is not a polynomial. And the reason it's not a polynomial is I see some division. I see some division by x in a polynomial. X's in denominators are not allowed. This is another example of something that's called a rational function. And the reason it's called a rational function is because there's a ratio. It's a thing divided by a thing. All right, next example. And I'll ask the exact same poll, which this next one is this a polynomial? That is, could it theoretically be rewritten as a sum of a bunch of constant coefficients multiplied by non-negative powers of x? That didn't take long, and it's pretty universal. Yeah, it's a polynomial. And in fact, the degree is 3, because the biggest power on x you would see if you did expand this out would be x cubed. All right. And 2 to the x, same pull again. Is 2 to the x a polynomial? All right, let's take a look. Let's see if it satisfies the definitions. So is this thing a sum? Well, it's a sum of one thing, so you can think of it as a sum. That's not the problem. Of a bunch of constant coefficients. Well, maybe it's like 1 times something of non-negative integer powers of x. So let's see if it satisfies. So a polynomial is a sum of things like, and I'm going to do some color coding, x to the p, where p is a power. X to a number, where that number is the power on x. So notice, the thing I see here is like the opposite. I see an x in the numerator and a number as the base of an exponent. 2 to the x is not a polynomial. I'm not allowed to see x's in the powers. I'm allowed to see x's as the bases in the powers. Integer powers of x's are allowed. Nice. So these were intended to each demonstrate different subtleties in the definition of what is and isn't a polynomial. A polynomial is only things that are powers of x. So x raised to an integer power. Groovy. So the next thing I want to do is, so because of weird versions issues, when I printed, I didn't actually print the correct version. You don't see these graphs on your piece of paper. Here are the graphs of some polynomials. X cubed, x times 2x squared plus 1, x times 1 minus 3x times x plus 1, and x times x minus 1 quantity squared. And let's analyze these in 2 ways. Let's analyze them in terms of the number of roots and turning points. Let's also look at their graphs and zoom out on them and see what their graphs generally look like. So let's start with these small window graphs. We know what x cubed looks like. Y equals x cubed has 1 root and 0 turning points. It never turns around, and it crosses the x-axis once. Here's the graph of x times 2x squared plus 1. And, well, it looks an awful lot like y equals x cubed. It has 1 root. That 1 root is at x equals 0. It has 0 turning points. But if you zoom in close to that root, you see something interesting there. It looks like if you want to compute the slope, the slope at 0 is positive. Y equals x cubed doesn't have that. If you want to compute the slope there, the slope zeroes out. So there is a difference between them. Let's take a look at this next graph. X times 1 minus 1/3 x times x plus 1. So this time I see 3 x-intercepts. In fact, that's generically what you would expect for a degree 3 polynomial. How many turning points does it seem to have? How many times does it turn around? And if you want to answer, go ahead and put it in the chat. How many turning points does this graph have? This is also just an opportunity to make sure everyone remembers what a turning point is. I see a 3 for the number of turning points. Well, let's count. So a turning point is a place where it goes from increasing to decreasing or decreasing to increasing. So let's count the number of turning points using that logic. So right here, it seems to be decreasing. So it decreases, it decreases, it decreases. It looks like right there, it starts increasing. So here it starts increasing. So that means that right here, this point right here is a turning point. It's a place where it changes from decreasing to increasing. It carry on until about x equals 2-ish, not exact. And then it starts decreasing again. So right here is another turning point. And then it's going to keep on decreasing forevermore. There are no more turning points that way, no more turning points that way. So I think I see 2 as the number of turning points. Does that seem sensible? All right, and this last one, x times x minus 1 squared, same question. I think I see 2 roots. And the number of turning points, well, let's see, it is increasing, 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 increasing. There's a turning point, and then it starts decreasing very little bit. And then there's another turning point, and it starts increasing. I see 2 turning points. Any questions about that quick reminder about what turning points are? All right, so let's summarize those facts. So here's some truths about polynomials in general. Any degree d polynomial will have at most d zeros. And we've seen that in practice. Right? What's a degree 1 polynomial? Well, it'll have at most 1 x-intercept. There will be at most 1 0. Exactly 1, in fact. A degree 2 polynomial will have at most 2 x-intercepts. A degree 3 polynomial, as we've just seen, can have up to 3. It turns out that's the most. Degree 4 polynomial at most 4, degree 5 at most 5. A degree d polynomial will also have at most d minus 1 turning points. And so we've seen that also in practice. A line never turns around. When degree is 1, there are no turning points. When the degree is 2, there's 1 turning point. Degree 3, we've seen that there can be up to 2 turning points. Sometimes there are fewer. All right, cool. So the next thing to mention is what happens when you zoom out on a polynomial. And while these graphs do appear here, I think the right way to see this is by seeing actual Desmos graphs. And I apologize for this versions issue that resulted in this not printing correctly. Let's check out a Desmos link to exactly these things graphed. Oh, come down. Wrong one. Okay. I'll take this and zoom out. Negative 100 to x equals 100 y-axis from negative 1, 1, 2, 3, 4, 5, 6, 2, 1, 1, 2, 3, 4, 5, 6. Sorry, I thought I set this up correctly beforehand. All right, so we see here these graphs zoomed out. Let's just start with x cubed. X cubed looks like x cubed. It turns out as long as you control the viewing window correctly, X cubed is very stable at various viewing zooms. It'll always just look like X cubed. Here we see the graph of X times 2X squared plus 1. In looking at these two graphs, how does it roughly look like they compare? How does blue compare with red? Don't try to look at the formulas, just look at the graph. If you were to see these two graphs, what approximately seems to be the difference between them? Blue has a steeper slope. In general, the whole thing looks steeper. And maybe it's hard to see exactly here. Well, you can see something reasonably exact. It turns out it's about twice as steep. All of the y values are just about doubled. Right? I see a y value at 68 of 314, a y value of 68 of about double 314. Not exact, but pretty close. In general, I'm going to go back to now this. The difference between these two graphs is the y values about double. So this is about 2x cubed when you zoom out far enough. Let's pull up the next one. Click, click. All right, so this next one, that 3 doesn't need to have parentheses around it. That's a weird Desmos issue. How do these two graphs compare? I think while people think about that, I'm going to zoom out further. Let's stick one more 0 there. One more 0 there. 3 more zeros there. So you want to see those two graphs. How do the y values compare between the two? What transformation goes from red to green does it look like? I'm going too slow. So it looks kind of like green is compressed a bit. It's been squeezed down, and then it's also been flipped vertically. So let's write that down. So to go from here to there, it looks like this has been compressed vertically and also flip vertically. And the takeaway here is that this is about the same as negative 1/3 x cubed. The negative for the flip and the 1/3 for the compression. This next one, x cubed minus 2x squared plus x, that's about the same as x cubed. If we pull up the Desmos graph, at this viewing window, those two seem to be exactly on top of each other. You can't visually tell the difference. So what's the takeaway here? The takeaway is if you graph any degree d polynomial and zoom out sufficiently far, it will just look like the graph of a d x to the d. So if you see a degree d polynomial and you want to know what the graph looks like, when you zoom out far enough, you'll just see the leading term. And maybe I'll write that in an example. So if you want to graph negative 7x to the 5th plus 3x to the 4th minus 2x cubed plus x minus 1, this is pretty close to just being negative 7x to the 5th when you zoom out. So for really big x values, this is basically just the leading term. Nice. So what I'm going to do with my remaining time is let's put these facts together and do a little bit of graphing. So I think I want to jump straight to this next example. So on the previous page, we looked at the graph of x times x minus 1 quantity squared. So we saw it had two x-intercepts. There was one there and one there. One at x equals 0. That's this one. And one at x equals 1. This one. But those two x-intercepts, they look really different. This intercept at x equals 0, it looks like it goes straight through the x-axis. If you zoom in close to x equals 0, you zoom in far enough, you'll see basically a straight line. And we can pull up a quick Desmos demo of that. There it is. And now we can, oh, that's not the one I want. I want this one. Let's zoom in really close to x equals 0 and see what happens. So I'm zooming in, I'm zooming in, I'm zooming in. Yeah, that looks like a straight line. If you zoom in far enough on this graph, you just see a straight line. If you look near x equals 1, instead, well, you can see it even at this scale. If you only saw that much of the graph, you would say that looks like a parabola. It turns out that's true for any polynomial. Once you have a polynomial factor, you can read off what its graph looks like. If you have a polynomial of the form q of x times x minus c to the power p, so I know that sounds abstract, but let's write it this way. This polynomial is of the form p of x equals something that is not equal to 0 when you plug in x equals c times another piece, which is equal to 0 when you plug in x equals c. So once you factor a polynomial like that, then you can graph. So then let's just finish the sentence. So then, close to x equals c, the graph of p of x will look like q of c times x minus c to the power p. So what have I done? I've taken the bit that's written in green, when the bit that is not 0 when you plug in x equals c. And what have I done? I've plugged in x equals c. And this other part, the part that's equal to 0 when you do plug in x equals c, that bit I just have to remember. So if you want to graph a polynomial near an x-intercept, you can by following this rule. And this lets you get a pretty good idea about what the graph of any polynomial will look like. So with my remaining 6 minutes, let's use this tool to graph some polynomials by hand, entirely by hand. So here is a polynomial. It sure looks like this is degree 6, because this will kick out an x to the 1. This will kick out an x squared term. This will kick out an x cubed term. 1 plus 2 plus 3 is 6. This is a degree 6 polynomial. It's factored already, so it's easy to find the zeros. So step 1, find the zeros. If you find the zeros, that'll be x times x plus 1 squared times x minus 2 cubed equals 0. And once you have something that's factored, it's really easy to set it equal to 0. Just one of the factors has to be 0. Nice. Okay, so that means that 0, 0 is one of the roots. Negative 1, 0 is one of the roots. I guess if I'm calling them by points, they should be x-intercepts. And one of the x-intercepts is at 2, 0. Nice. So We have found each of the zeros and indicated them on the graph. I said not to worry too much about scale, but that looks about right. The result of this previous statement, this, says that if I want to factor close to one of those roots, I should remember the part that actually gives me the 0. And to the rest of the parts of the polynomial, I should just plug in x equals c. So let's do that. If I write down y equals x times x plus 1 squared times x minus 2 cubed, the rule on the previous page says I need to remember the x, so I'll write down x. This piece, when I plug in x equals 0, I get 1. So I should just plug in x equals 0 and get 1. Plug in x equals 1 to here, and let's write down what we get. It looks like we get x times 1 times negative 2 cubed. I think that simplifies to negative 8x. So that means close to x equals 0, I should see basically negative 8x. So let's graph that. Close to x equals negative 1, I'll do the same thing. Y will be, well, y is equal to x times x plus 1 squared times x minus 2 cubed. This time, consistent underlining I think would be nice. Here's the piece that gives me the 0 at x equals negative 1. So I need to remember that piece. Now I'll just plug in x equals negative 1 for the rest of them. So what do I end up with when I do that? I get x plus 1 squared times negative 1 times negative 3 cubed. I think that's 27x squared. Nice. So close to this point, I should see an upward opening parabola. It'll be scaled up by like a lot, but I'm not worrying about scale in this example. I just want to get the right cartoon of the graph. Finally, near x equals 2, I should see 2 times 3 squared times x minus 2 cubed. And if I can do arithmetic, I think that that is 18x minus 2 cubed. So I should see something that looks like x cubed shifted to the right by 2. And then I should see it stretched by a factor of 18. So I should see something that looks something like this, close to x equals 2. To get the rest of the graph, I will interpolate smoothly between. For big x values, this is basically just x to the 6th. To see that, take this and imagine you want to expand it out and only recover the biggest term. That'll be x times x squared times x cubed. Yeah, x to the 6th. So for big x values, this function will basically look like x to the 6th. Neato. So with my remaining minute, let's pull up a graph of exactly that and just see how it looks. All right, so let's graph x times x minus 1. Oh, times x plus 2 cubed, and go to a normal viewing window. Yeah, I think that qualitatively looks about right. We see, as we wanted to see, a little parabola going on here. Oh, I changed all of these signs. I'm sorry. Plus, this one was a minus. All right, that's better. I see a little parabola here at negative 1. I see a straight line, pretty steep at 0, and then a cubic at x equals 2, which is what I expected. Groovy. So with that, I think I'm about at time. So I'll go ahead and call it there. There's another example on this page I'll encourage people to give this next example a look and decide if you want to see this next example talked through at the start of lecture next time. Cool. So I'll see you all in person tomorrow. I hope you have a good day and stay warm. I guess I'll be here for a few minutes if you have any questions.
If I, let me just pull it up. It is the
Oh.
one due for tomorrow.